Very good. Thank you so much and welcome to the Mineralization Summit. So I'm going to go through a little bit of the technology and give you a little bit of an introduction and hopefully a historical context as well, and sort of go through the challenges. See if this works. Okay, but I wanted to start with sort of a global stock take on the carbon reservoirs on Earth. Where is our carbon? So we have a lot of carbon stored in the oceans. Okay, so the oceans are a really, really big carbon reservoir, and they take up about a third of the carbon that is actually emitted by humans, which has the consequence of ocean acidification. But the biosphere, in contrast, is a much smaller carbon reservoir. It's big nevertheless, so this is trees, vegetation, soil, everything, you and me. But the smallest of these three is actually the atmosphere. Although there is, of course, too much carbon in the atmosphere, which is causing global warming, but it is the smallest of the reservoirs. However, these reservoirs are dwarfed by the by far largest reservoir on Earth, which is rocks. So over 99.9% of all carbon on Earth is naturally stored in rocks. So natural rock weathering removes about a half a gigaton or a gigaton from CO2 from the atmosphere every year. But it's not surprising that we want to return some of our human-emitted carbon back into this largest reservoir on Earth, from which most of the CO2 came already in the form of fossil fuels in the first place. So we talked about earlier the volcanic eruptions in the Reykjanes Peninsula. So the town of Grindavík is actually a little bit south of this. So these are about the youngest rocks on Earth. And you can actually see Reykjavik city here in the background. So it's not very far from Reykjavik. And I also have with me, because I know a lot of you came a long way to visit Iceland, and you won't all be able to visit there, so I took a few rocks with me from this volcanic eruption. So please, come up here and touch some of the youngest rocks on Earth. And for those of you who actually remember the volcanic eruption 10 years ago from Eyjafjallajökull, if you thought that was hard to pronounce Eyjafjallajökull, I proudly present to you Sundhnúkagígaröðin. I expect all of you to be able to pronounce this by the end of the summit. But CO2 and carbon is emitted naturally into the atmosphere in volcanic eruptions. And this process is just a part of the long carbon cycle which nature has regulated for millions of years. But we have disrupted this cycle by our relentless emissions of fossil fuels emissions. But what happens right after the eruption starts, nature starts cleaning up after itself. So these rocks will start naturally binding carbon. So one of these mechanisms is just as simple as CO2 in the atmosphere dissolves in raindrops, rain falls on the lava and seeps into the rocks, and it starts forming slowly solid carbonate minerals in the rocks. The problem is, of course, that nature does this really, really slowly. And so we need to speed this up. And this is what Carbfix has done. So we use basalt and other reactive rock formations, very rich in these metals, these divalent cations, calcium, magnesium, and iron. We dissolve CO2 in water. We make sparkling water, essentially. And we form solid carbonate minerals in the pore spaces of these rocks. And because this is a mineralization summit, I should sort of summarize some of the other pathways on how you mineralize CO2. So Carbfix does this. This is in situ or underground storage of CO2. So in situ, that you're actually operating and storing your carbon in the same place. But we also have other methods that do the same things or cause the same reactions. So we also have ex situ, and that's above ground. So you have some alkaline feedstocks that is rich in these metals, and this alkaline feedstock can be, for example, industrial waste, such as cement kiln dust, steel slag, or fly ash. And you react it with concentrated sources of CO2 in specific reactors. And you can actually precipitate the carbonates out in reactors and use them to actually produce valuable goods. In this case, they're showing here outputs like carbonated concrete, which not only makes the concrete stronger, but also has the benefit of storing the CO2 permanently. Then we have other types of above-ground mineralization, such as this is, I think, mine tailings. So basically, you have your alkaline feedstock, and this can be also in the form of crushed rocks. So when we are mining for platinum, nickel, etc., we usually end up with a lot of waste rock, which is in many cases powderized. And so you can actually stir up this material on the ground to actually have it react with ambient CO2 in the atmosphere. And this is, for example, what the company Arca is doing, using mine tailings to react, to make it react with CO2 in the atmosphere. And we'll actually hear more about some of these methods tomorrow in Marco Mazzotti's talk. But lastly, we also have enhanced rock weathering. So basically, this is taking crushed rocks, for example, olivine or serpentine, or basalts, and spreading them across either croplands or enhancing the alkalinity in the ocean. So enhancing the ocean's ability to actually bind more CO2. So this is reacting either with the ambient CO2 or the CO2 already dissolved in the oceans. Okay, so these are the pathways. And just a throwback to last year's Mineralization Summit when we had the pleasure of having Klaus Lachner give a great talk. So he was one of the first to suggest the use of mineralization as a climate solution. So he's also widely considered as being the father of the direct air capture. So he called it the mechanical tree. But he was also one of the first to suggest mineralization to combat climate change. And in 1995, he published this paper, Carbon Dioxide Disposal in Carbonate Minerals, which he reviewed last year. But there they were thinking of ex-situ mineralization. So using crushed rocks, mainly olivine and serpentine, and to dispose of CO2 from coal-fired power plants in reactors. So that was the premise of this paper. But they also mentioned this possibility of underground storage of CO2. Here in the paper, they say a variant of the direct carbonation would be to pump CO2 directly into an underground deposit of porous magnesium or calcium-bearing rock. Okay? So they recognized immediately why this would be nice, because you use the entire underground formation as your reactor, so you have a vast capacity. And you also have much more time to do it. You can let it lie there and sit for rapid mineralization instead of having to move very, very quickly with reactors. But they also point out this difficulty here, that the major difficulty lies in finding deposits that are sealed to the outside, yet allow transport of the CO2 throughout the deposit without cementing in and sealing the injection well. So essentially, this is what Carbfix solved. And how is it solved? Here's a famous image from Erik Ölkes and Gíslason, 2014, comparing conventional storage of CO2 in sedimentary rocks, injecting pure CO2 in supercritical forms deep into saline aquifers or depleted oil and gas fields. For this, because it's a buoyant phase, we need an impermeable caprock to keep the CO2 plume in place. In Carbfix, however, or in this depiction of Carbfix and how it was done originally, we essentially make SodaStream. So this is a SodaStream machine. We sparge the CO2 in gaseous phase in an outer pipe in water. So we mix the CO2 with water going down into the formation. And by the time, and here are, for those of you interested, here are sort of the chemical reactions. We dissolve it and we create carbonic acid, essentially. And as the bubbles travel down, they experience a buoyancy force, but this buoyancy force needs to be counteracted by a drag force, that the velocity of the water that takes them down. So you must tune your system in such a way that all of your CO2 is fully dissolved in the water before it enters the formation. by the end of the casing. And so when the CO2 enters the formation, it's fully dissolved in water, and it has no tendency to rise. So we call this solubility trapping. And as soon as the CO2 in aqueous phase or dissolved CO2 hits the rock, it starts attacking the rock. So the acid produced by the carbonic acid starts actually releasing these metals out of the rocks. And basalts are examples of rocks that are very rich in these metals. And these metals start to being leached out into the fluid. And what happens is that then the pH rises, the acidity goes down, and you have and you create the conditions for precipitating carbonate minerals away from the injection well. So this is really important, that these dissolution reactions, they are dominating close to the injection well. So we're actually creating permeability. We're not clogging up anything close to the injection wells. And in the 10 years of experience of Carbfix, we have never really encountered an increase in injectivity in our wells. We rather experience the opposite, that the injectivity is increasing. And if we keep comparing these methods, because most people in this space would be familiar with the conventional injection of CO2 in supercritical phase into these deep saline aquifers or oil and gas fields. What happens there is that from day one, you need this structural and stratigraphical trapping. That is sort of the impermeable cap rock in the formation, or the umbrella that is keeping the CO2 in place so it doesn't leak back up, because it is buoyant. So this is increasing storage security to the right and trapping contribution as a function of time. And as time goes by, we will have more residual trapping. So this is CO2 that becomes trapped between the grains, sort of like a sponge effect. And in time, more and more will actually be trapped in solubility, so in the formation waters that are already in the underground. And in some, depending on the rock compositions, you might have some mineral trapping, but look, the timescales are thousands to 10,000 years here. If you compare this to injection of dissolved CO2 into reactive rocks, you have almost instant solubility trapping. So you reach the next safest trapping mechanism from the start. And then very rapidly, and you can say the timescales here are very different from these ones. So in a matter of months or years, you are precipitating carbonates and you're creating the solid minerals, and you have full mineral trapping within months or years. But of course, this comes at the cost of water use. So here's a graph from Snæbjörnsdóttir paper 2020. Showing the water demand for this. So you need a lot of water to actually dissolve a ton of CO2. And if we just take the typical operation pressures here from 20 to 60 bar, we can see that for each ton of water, you're going to need about 20 to 30 tons of water. Sorry, for each ton of CO2, you're going to need about 20 to 30 tons of water. Now you can use seawater in places where you have access to seawater in coastal areas, or you could use some saline formation water, brackish water, non-potable water, so you don't need to be competing with potable water from the local environment. And actually, if you use saline water, you can see that it's almost as soluble. You don't need much more of it than fresh water. So this is definitely a possibility. And we are actually trialing this technology out in Helgavík, in a place very close to the airport, where we are injecting seawater dissolved CO2. So if we want this technology to scale, then it's clear that standardized methods and high quality measurement, reporting, and verification protocols must be in place, and you must apply them across the project and just to measure how much the project has removed or stored. So this is an image from one of our methodology documents, which sort of depicts how and defines the boundaries and where we measure things. But it shows you that we are pretty much using injection wells and nearby monitoring wells to verify the fate of the CO2. So we use basically aqueous chemistry. This is a very active R&D front, and we are developing complementary methods to verify the fate of the CO2. But the primary means of verifying today is still by using chemical tracers for the most part. Things have been automated to some extent, but we are still sending people in the field to take samples of what's happening in the reservoir. And so this is one of the most famous examples of this. This is dissolved inorganic carbon as a function of time in the original Carbfix pilot. So this is a 2016 science paper that many of you here in the room contributed to. So this is actually showing what we measured in terms of dissolved inorganic carbon, and then what we actually expected to see in the monitoring well based on non-reactive tracers. So a non-reactive tracer is something that does not go into the carbonates, doesn't react with anything, but we don't see this, we see this. And so the difference between these two curves is about 98%. We can say that we have mineralized at least 98% of the CO2, or more than 98% of the CO2 is actually missing from the injection to the monitoring well. And so you might ask, do you have more proof? And in this case, yes, we did. This is a submersible pump that was installed in the monitoring well, and it actually stopped working after a while. And when it was hauled back to the surface, we saw exactly why it stopped working. It was littered with these carbonate precipitates on the pump itself. And so this is actual physical evidence because we found our tracer in these calcites. These were calcites mostly. And we actually recently gone back to this and to measure the isotopic abundance of these carbonates. But here it is. You can touch it. It's real. So here's a clip from a newspaper back in 2006. January 2006, and I will just read it to you and translate it to English. Iceland can become a pioneer in carbon storage. So here we have, for example, a very young version of Jörg Matter, who is somewhere here in the audience. We have Siggi, Erik, and here is former president of Iceland, Ólafur Ragnar Grímsson. And the one giving the talk is Wally Broker. And so Wally, I'm told, was very instrumental in sort of pulling everyone together, most notably Columbia scientists and Icelandic scientists, and to form the Carbfix project. And so this is sort of the start of it here in Iceland, at least. So Wally passed away a few years ago. He was a titan in climate science. For example, he was one of the first guys to actually raise the red flags against climate change. This is a paper from 1975, in which he writes, the exponential rise in the atmospheric carbon dioxide content will tend to become a significant factor, and by the early in the next century, we will have driven the mean planetary temperature beyond the limits experienced during the last 1,000 years. And if you look at some of the predictions he's making there, they are scarily accurate. He also wrote this popular book, and I am told by some old-time Carbfixers that the inspiration of the name Fix in Carbfix didn't only refer to fixation, but also this title, Fixing the Climate Change. So fix as in fixing. Okay, so I'm not going to go further into like the history of Carbfix, how we did like our pilots and all the people that contributed to it, a lot of postdocs, PhDs, through experiments, pilot injections, etc. but I'm just going to show you pictures from the field. These were all taken within the last year. So what you can see here is that we are just very active on many fronts. We have a lot of projects in the field in Iceland and are preparing projects elsewhere in the world as well. So this is the Mammoth injection well. This is us when we were drilling the injection wells for Mammoth, which is Climeworks' direct air capture facility. Here you sometimes need to put on skis when you want to go sampling. This is from seastone when we're sampling the seawater, drilling seastone and monitoring flux in the field, or at least I think so, looking at the Ghostbusters outfit. Okay, but why do we want to do mineralization? So in a world with a long history and skill set in conventional CO2 storage, what can mineralization bring to the table? And I can sort of think of at least 3 points. That number one, we of course want to leverage the unique benefits of mineral storage. And this is that it's permanent, it's very scalable, it's verifiable, it's safe, and it's environmentally friendly. And in most cases, it's very, very cost effective as well. Last but not least, we also want to bring this tool to regions that don't have access to conventional storage. As you can see, this is a map of the United States from this recent Lawrence Livermore National Laboratory report. And as you can see, the highlighted regions here, the pink regions are the rocks that would be favorable for mineralizations. They are very sort of anti-correlated with the conventional storage. So they are bringing access to carbon storage that otherwise don't have the opportunities. And you can think that it could compete directly with conventional storage, although I think that this should probably not be the focus. But you can also see on this picture here, so this is cost per ton of CO2, given a bunch of assumptions, I guess. And you can see, like in some regions in the United States, we're reaching like $10 per ton at scale. But you can also ask yourself, where is the pink scale? Where is the scale of the cost of mineralization? And that is missing, not because the authors were lazy, but because we don't have enough data to depict it. We know it's very, very cost effective here in Iceland. But we just don't have enough of these projects and enough data, especially projects at scale, to be able to actually put a number on it. Although we have done it very cost effectively here in Iceland. And last but not least, I would say, like in many countries, you don't know exactly how these will be permitted. And what you can do and what you should do needs to be known if you want to put a price tag on it. Now, if we think beyond Iceland, we have favorable rocks spread in every continent. The storage potential has been estimated somewhere in the hundreds of thousands of gigatons of CO2, so much larger than we will ever need. But it's never really the storage capacity that is the limiting factor. It is rather related to other factors. For example, logistical considerations, such as capture and transport of the CO2, so the supply of the CO2. And this is in turn constrained by lack of market and policy. And second, unlocking a storage resource can have long lead times due to extensive characterization work that needs to be done to reduce uncertainties and minimize risk. So the highlighted regions you see here in the Carbfix mineralization atlas, they are by no means equally feasible. Many of them are not feasible at all. So the applicability of mineralization is still very location specific, even within the highlighted regions. So exploration is a big part of what we need to be doing. These are examples of favorable rocks that have been focused on so far. So we have volcanic basalts, which are mafic rocks, and then this is serpentinized peridotite in British Columbia. So we know that both of these rock types react very rapidly with CO2. But even within these categories of rock types, they can be vastly different. For example, here we have extremely porous young basaltic rocks, for example, the ones that are here on the stage. But we can also have basalts that is very old and very dense. So we need to be characterizing it. And we also can have some other types of igneous rocks in between, volcanoclastic rocks or other types. But chemical reactivities, reactive surface area, age, alteration states, this all needs to be characterized, and which also brings us to permeability. This is Hengifoss in East Iceland. But when you inject your fluid, it needs to be transmitted effectively in the underground. In this configuration, we have permeable zones here in between the layers of these flat basalts. And so if this would be the underground, the fluids would be transmitted effectively here between these layers. We also might have some vertical permeability here in these layers in between. And then we have a more slow, uniform flow of fluid in the porous rocks. So this is always needed if you want to push a lot of fluid into the subsurface. And then you must choose how are you going to inject. And these two methods have been tested in the field. So you can have water-dissolved CO2, like we have done, or you can have pure CO2 injection or supercritical CO2 injections into basalts, which is what they tried in Wallula in Washington State, USA. So water-dissolved CO2, it is non-buoyant, so it's trapped in solution, and it has no tendency to rise. So you don't need to characterize cap rocks or fractures. It requires a lot of water, so 20 to 30 tons of water per ton of CO2. So if it requires so much water, then more wells will be needed for a given volume of CO2, typically. It is less viscous than CO2, so it doesn't flow as effectively. There is great operational flexibility in this, however. We can very easily stop the injection of CO2 and put back on, so intermittency is not an issue. And also, when you have a multi-well operation, you can sort of divert your flow into functioning wells if you need to service or do something to malfunctioning wells. So operational flexibility is a plus. And we have robust MRV, or measurement, reporting, and verification techniques already developed. We do have the problem of corrosion, and must choose our materials carefully. And this has now been tried in several places in the world. So 4 places in Iceland, at least. We have 4401 doing it in Oman and United Arab Emirates. We have a recent pilot in Saudi Arabia. We have activity in New Zealand, and Carbfix was a member of a project that injected into volcanic clastic rocks in Turkey. Now, if you go to pure CO2 injection, now that is a buoyant phase. You need a minimum depth of 800 meters. You need to characterize cap rocks and fractures to keep the CO2 in place. This would be more geographically constrained because in basalts, you don't always have these cap rocks. You definitely have them in the Columbia River basalts in the Pacific Northwest and in other places. But when you go to, for example, Iceland or Hawaii or Japan, you might not have these. Permitting might be more mature in some countries that already have some regulatory framework around conventional injection, but we've made a lot of progress there with respect to, for example, Europe. Monitoring techniques are still being developed. It's unclear if they will follow more or less the same monitoring techniques that are used for conventional injection, and there's a question of reactivity times. We don't have a very good understanding, at least on the reservoir scale, where these would be precipitating and for how long you could sustain the injection. But a lot of work is being done in this space. But to summarize all this, we need more field demonstrations. More pilots are needed to provide learnings from different sites and scales, allowing us to assess potential uncertainties and reduce risks. And that is exactly what Carbfix is trying to facilitate. So this is Nespresso it is a pilot capture plant that is operating in Nesjavellir, capturing CO2 from an impure gas stream of a nearby power plant. So it has everything contained within this 40-foot container. And it's also available for pure streams. So you can actually place a system like this on top of an injection well, and then it's a question of plug and play. So these mobile units can be actually crucial to unlock new sites and answer important questions before a commercial scale-up. Interestingly, I would say, like, this is actually what we are venting at the top here is almost like pure hydrogen. So we're actually producing geological hydrogen. And we will have a talk tomorrow about like nice co-benefits of mineralization. But I think despite all these challenges, I think it's really important to keep in mind that we have a commercially ready technology that has been proven and certified. When you look across the playing field of climate solutions, we have come quite far. And there's a lot of scientific literature behind this, much of which has been produced by people sitting in this room. And in the words of Klaus Lachner last year, mineralization has the largest capacity, the most stable form, and is the most, and in most forms, readily verifiable. So we have a good product. And since 2014, we have injected over 100,000 tons of CO2. So that is something, and something to build on. And just look where we've come so far. We've already achieved scale-up. So both these facilities, actually, Mammoth and Silverstone, will be a part of the field trip tomorrow. So compared to last year, we will have new stuff on display. But these aren't even like the first scale-ups. These are not 2.0s. These are 3.0. Because look where we started. This is the Arctic Fox Climeworks unit, 50-ton capacity installed in 2017. And now we have Mammoth. And this is Gertrud, the first pilot capture plant of Carbfix back in 2012. And we have achieved two times scale-up of this. So now we are actually capturing over 95%, or will be capturing 95% of the CO2 coming from the power plant. So in 2025, when these systems are fully commissioned, we will have a capacity of 80,000 tons per year. So you see, it's only going to take like a little more than a year for us to overtake everything we've done in the last 10 years. So that's already progress. And hopefully we won't stop there. We will have the Kota Terminal, a first-of-a-kind transport and mineral storage hub, which received 115 million from the European Innovation Fund. So we live in a world where climate solutions are desperately needed. So we must all help build up the ecosystem that allows them to thrive. And this is a really, really good solution. So here at the summit, we have people from advocacy groups, policymakers, financiers, regulators, industrial players, startups, and think tanks. We are all here. So let's make good use of this time. Let's ask questions, share knowledge, form collaborations, and move mineralization forward. Thank you very much.